In our last video, we took a little look at ethane, very simple molecule, and looked at Neumann projections for the eclipsed and staggered conformations for ethane. In this one, we're going to look at a slightly larger and more interesting molecule, butane, which is still pretty simple by molecule standards. And the reason that this is going to be more interesting is because in the ethane molecule, we have two carbons, and when we look down the CC axis, we can see 6 hydrogens attached to those two carbons. Since every single group there is just a hydrogen, it's very symmetric. There's not a lot of variety in how things can be oriented. Essentially, eclipsed and staggered were the two interesting conformations. Now when you go to butane, and what the interesting axis we're going to look down is we're going to look down the C2, C3 axis. So right here, I have butane, 1, 2, 3, 4 carbons, 1, 2, 3, 4 carbons, and if I look down the C2, C3 axis, I can see what 3 things are attached on C2 in the front, which 3 things are attached to C3 in the back. So oriented the molecule so that it's appropriate for a Neumann projection. There we go, we're looking directly at C2. C2 is right there. C1 is pointing essentially straight up and towards us. This is closer to us than C2. C3 is hiding in back. So if I've got that oriented just right, you can't see C3 at all, but you know it's there because you can see what's attached to it. So here's a staggered conformation of butane. So notice if you're mastered, eclipsed, and staggered from the last video in our look at ethane, you can see that this is staggered. And if I go to draw the Neumann projection, I draw a circle representing the second carbon. I've got the first carbon, the methyl group there, pointing straight up, and the 2 hydrogens that are also on the second carbon pointing down. If I'm going to do a Neumann projection for something, I find it extremely useful to draw out a Lewis structure so I can see what's attached to the atoms I'm trying to represent. So if I look at the butane here, I draw the 4 carbons in a row. And if I look at C2, has a hydrogen, a methyl, and a hydrogen attached to it. So those are the things I draw here, a hydrogen, a methyl, and a hydrogen. And then C3, which is in the back, also has a hydrogen, and a methyl in there. And if I have a model and I orient it in the staggered conformation and I look down the appropriate axis, so there I go down the C2, C3 axis, you can see methyl pointing straight up, 2 hydrogens pointing down, and then on the back carbon I'm holding methyl, which is C4, so straight down on the back carbon is a methyl that I'm holding, and then up and away from us are the 2 other hydrogens. So this conformation is particularly stable and is typically how we draw the skeletal structure for these guys with a little zigzag like this, because it makes the first carbon as far apart from the 4th carbon as it could be. It's the greatest distance apart. So this is a staggered conformation, and it's also called anti, or anti, I guess, because the 2 largest groups attached to the axis we're looking at, so we're looking at the C2, C3 axis, carbon 1 and carbon 4, those 2 methyl groups, are now as far apart from each other as they can get. So when the 2 big groups attached to the carbon 2, carbon 3 axis are as far apart as possible, that's called anti, and that is the lowest energy configuration. So the very lowest energy configuration. If we then visualize keeping the front carbon in exactly the same place, right? So I have C2 stays in exactly the same place. So carbon 1 is up. The 2 hydrogens on carbon 2 are down and to the sides, and all those 3 things are pointing towards us. So I'm going to envision holding this. So I have C2 I'm looking at, C1 is up, two hydrogens are down. Now I can have free rotation about C3, and this is really hard to visualize unless you can do it yourself in some sense. But I'm going to rotate the back carbon 60 degrees. And so I envisioned moving the substituents in the back carbon 60 degrees. And that's just the right distance to go to an eclipsed conformation. And again, it's like getting this perfectly eclipsed and then getting the camera angle just right is really difficult. But there it is. The methyl was down here. I rotated everything on the back carbon, including the back carbon, 60 degrees, which brought the methyl completely in line with the hydrogen. So that makes this an eclipsed conformation. And then the hydrogen that was here rotated around to hide behind that methyl. Then this hydrogen rotated around to hide behind that hydrogen. So this eclipsed conformation is now going to be higher in energy than the staggered conformation, because now groups are getting closer together and there's going to be some repulsion between their bonds. Now if I continue to rotate there, and I have the stuff on the back carbon rotate another 60 degrees, again the stuff on the front carbon I'm keeping in exactly the same place to keep it mentally simple. If more things stay the same, it's less active thinking. But now I'm going to move the methyl on the back carbon, carbon 4, is going to continue its journey, and that'll bring us into another staggered configuration. So we had this eclipsed conformation. Now watch as I rotate here, this carbon can get staggered in between those guys. There we go. So this is the Neumann projection, the molecule depicted by this Neumann projection. And it's the same molecule, it's just changing its appearance based on the free rotation around the single bond. So again, getting the camera angle right so that you can see that's staggered. And now the methyl in the back carbon is pointing away from us between two other groups. So there he is, methyl in the back. And this relationship is starting to get a little higher in energy because these two methyls are getting closer to each other and starting to repel each other. They can almost bump if those methyls start rotating around their axes. So this one is a staggered conformation as well. We're going to use the word gauche to represent that the two large groups are closer to each other in a staggered conformation and are not opposite each other like they were when they're anti. So there's a little more repulsion there. And I refer this one as the lower energy group because it's staggered, it's lower in energy, but it's not as low energy as when the groups are as far apart from each other as possible. So a little repulsion between these groups raises the gauche a little higher in energy than the anti. But those are both versions of staggered conformations. And then if we continue to rotate and go another 60 degrees, so there we go, you can see the gauche guys starting to get close. Again, I want to orient this so that the methyl is pointing straight up on the front carbon. Now I'm going to rotate another 60 degrees as best I can, and that brings things back into line. So if I move this back methyl and everything attached to it goes another 60 degrees, so carbon 2, rotate 60 degrees, and that means the methyl here is going to be perfectly lined up with the methyl behind it. And so here's another picture. Methyl in the front stays in place. Two hydrogens stay in place. Everything on C2, we're just leaving C2 and stuff attached to it alone. We rotate around C3 so that the methyl on C3 ends up straight behind the methyl on C2. And in some sense, it's a good idea to keep the numbering in place because it's carbon 1 is this guy. It's attached to carbon 2. Carbon 3 is hiding in back. And then carbon 4 is the methyl in the back, which is lined up with carbon 1. And you can see how close these guys are getting. If I put this on its side, notice these two, carbon 1 and carbon 4, are lined up. And now if these start rotating, these hydrogens will literally smack into each other. Stop touching me, stop touching me. So that's why it's higher in energy, because these two methyls, the two largest groups on C2 and C3 are the methyls, and now they're perfectly lined up and very close to each other. So this is again an eclipsed conformation, and many people will call this fully eclipsed because the two largest groups are now eclipsed with each other. And that makes this the highest energy of the butane conformations. So butane conformation where C1 is close to C4. And then if you continue to rotate the back carbon around, you'll get to another gauche configuration, where again those two methyls are staggered from each other but close. Then you'll go to an eclipsed, which is not fully eclipsed, like that. And then if you keep rotating, eventually you'll get to where we started, ta-da, with anti-staggered conformation. So there's essentially 4 sort of unique and very nice conformations of butane, which you can visualize with the Neumann projections: staggered and anti, staggered and gauche. So staggered, anti, staggered, gauche. Eclipsed, where the two largest groups are not lined up, slightly higher in energy, and fully eclipsed, where the two largest groups on C2 and C3 are lined up. And it's fully eclipsed and the highest energy conformation. And I realize that when I'm making the video, this is not super professional, so chords get in the way, and molecules, when I first hold them up, are at some uninterpretable, strange angle. But bear with me and try to keep your focus on what we're trying to show here. So there we go, C2 in the front, C1 pointing straight up, C3 in the back, C4 pointing down and back away from us. And that is the anti-staggered and brings C4 very far from C1. No repulsions, low in energy. You can also read about this stuff in the book, and hopefully this is clear. We also have the other video that we made in the classroom with Gilbert, who did a great job editing those. Between both of these videos, I think you probably are going to understand this stuff pretty well. If you have any questions, feel free to shoot me an email and I will try to clear up what I can.